Hello friends, and welcome to this session on permutation and combination. We have done into previous sessions we have understood what is permutation and combinations. We have studied various test cases. Today we would be doing two more test cases, which is circular permutations and distributions, right? So before beginning circular permutation, let's see how to arrange ABC on a bench, right? How do we do that? There can be 3 into 2 into 1, which is equal to 6, which is equal to 3 factorial ways, and these are the wayouts: ABC, ACB, BAC, BCA, CAB, and CBA, right? So now if we try to arrange them in circles, let's put them on a circle, right? So if this is a circle, we can put A here, B here, C here, right? The next one would be ACB, right? A here, C here, B here, then it would be BAC, B here, A here, and C here. So if you see this one and this one are same, right? This is A, C and B, and then A. This again is A, C and B, and then again A. So these two are not different, but they are identical. Let's go to the next one, which is BCA, right? B here, C here, and finally A here. It is identical to ABC, right? So it's ABC. In a clockwise sense, it is ABC, right? So if we plot the next two, we would see that they are similar to ABC or ACB. So we have only two different arrangements, which is ABC and ACB, which means that the number of arrangements would not be 3 factorial, but it would be 2, which is given by 3 minus 1 factorial, which is equal to 2 factorial, right? Which is equal to 2, right? So for a circular arrangement kind of problem, the number of ways of arranging n objects in a circle is given by n minus 1 factorial, right? Now in a necklace kind of problem, if we are making a necklace, we can turn it upside down, right? So which means that there is nothing called counterclockwise or clockwise sense, right? So the number of arrangements would decrease by half, and they would become 1 by 2 n minus 1 factorial, right? So this is all about the circular arrangements. I hope that you are clear about it. As far as the exam point of view is concerned, they are not that important. I didn't find any question in a CSAT or a bank PO kind of scenario, so I would say they are not that important. But nevertheless, let's do two questions on it, which says, in how many ways can 8 managers, 1 deputy manager, and a chairman be seated on a round table such that chairman is always between a deputy manager and a manager, right? So if you create a circle, right? Let's create a circle. A chairman is also always between chairman here, DM here, and obviously on the second neighborhood it always would be a manager, because only managers are left. So this eventually means that DM and C should always be together, right? This question eventually boils down to the fact that DM and C should always be together, right? So let's consider DM and C as one unit. So they are one unit. Apart from that, 8 managers are there. So we have 9 units. So 9 units can be arranged on a circle in 9 minus 1, which is equal to 8 factorial ways, right? And DM and C can arrange themselves in 2 ways, right? It would be DMC or CMD or CDM, which is equal to 8 factorial into 2, which comes out to be 80640. You don't have to calculate that, right? The software is doing it here for me, so let it be, right? So this is the solution for this problem. The next question says 4 girls and 4 boys are to be seated on a circular table alternatively, which means boy, girl, boy, girl. In how many ways can we do that? Let's firstly look in how many ways can we arrange 2 boys and 2 girls, right? So there are 4 seats. B1 here, G1, B2 and G2. The next would be G1 here, sorry, G2 here and G1 here. Whatever other combinations you would make would be similar to this. So what we are doing here is we are firstly arranging the boys. So there are 4 boys. In how many ways can be arranged in circle? They can be arranged in 3 factorial ways. Now post this, the girls are no longer in a circular, in an independent circle. The circle is now fixed by B1 boys, right? They are now earmarked by boys. So this is now equivalent to arrangement in a line, right? So arrangement in a line can be done in 4 factorial ways. So the total number of ways would be 144, right? I hope that you understood the fact that why we are doing 4 factorial here and not 3 factorial, because once the circle is earmarked by boys, the arrangements would not be identical, right? They would be different, right? So that's why we are doing 3 factorial into 4 factorial, right? So this is about circular arrangements. We would do more examples in our question sheets. The other important concept which we are going to do today is distribution of identical / different things, right? So imagine you have an ice cream and a candy. In how many ways can you distribute them amongst your 2 sons, right? So since the number of the number of things are also little and we have only 2 people to distribute them, let's make a table out of it, right? So if we have S1 and S2, and the first arrangement is we can divide AB, both getting BA, right? The another one can be AB and S2 gets nothing, right? So this is S2, or AB here, right? So the number of ways are 4, right? Now let's take 3 things. I think the next example talks about 3 things. So let's take and understand about 3 things. Right? So the number of people are still 2. He gets A, he gets BC. Now if he can get B, right? He would get AC, he would get C, he would get AB, right? So these can be the 3 1, and then opposite to this, he would get BC, he would get A, he would get AC, he would get B, and finally he would get AB and he would get C. Then he would get all the 3, the other would get none, the other would get all the 3 and he would get none. So how many ways? 1, 2, 3, 4, 5, 6, 7 and 8, right? So there are 8 ways. Now let's complicate it a bit. What if we have 3 people? Let's say we have to distribute 2 things, ice cream and chocolate, amongst 3 sons. How can we do it? Let's make a table again. So S1, S2 and S3. Let's have 2 things only, right? So A, B, right? Second A, B to him, right? The third would be A and B. The fourth would be AB. The fifth would be AB here. The sixth would be AB here, right? So, and what else can be possible? Can there be something else which is possible? Yes, there can be BA here, right? or there can be B and A here, and then there can be B and A here, right? What else? So nothing else is possible. So if you see, the number of arrangements are 1 2 3 4 5 6 7 8 and 9. 9 arrangements. So when the things are less, we can actually make a chart and count them, but the problem is we might forget to write some of the arrangements. So what are we doing here? If you see the ice cream, for example, if there are two people, can go to either Sun 1 or Sun 2. So there are two ways of distributing ice cream. Similarly, there are two ways of distributing a chocolate. So total number of ways becomes 4. Now if there are three people, there are three ways to distribute ice cream. Similarly, there are three ways to distribute chocolate. Total number of ways becomes 1. If there are three products, right? There is first and two people. The first product can be distributed in two ways, the second product can be distributed in two ways, and third again can be two ways, which means total of 8 ways, which we see in this one, right? In this one there were total of 8 ways. Now if we have n products which are to be distributed amongst r people, so n distinct products to be distributed amongst r people. So first can go in n ways, second again can go in r ways, third r, and fourth r. All these n product can go in r ways, giving rise to r raised to power n as the final solution. So mind you, if this is only eligible if we have n distinct products to be distributed among are distinct people. So if the case is this, then we would get the result as r raised to power n, right? So you can remember this result because this would come handy in solving lots of problems. Now imagine if you have three distinct ice creams, you have to distribute them amongst your two sons. How can you do it? So first ice cream can go in 2, second again in 2, and third again in 2, total 8 ways. Now things are little complicated. You have same ice creams, right? Which means rather than AB, you have AA. Let's see how do we do that. So again there are two sons, S1 and S2. So what is the first combination? This is AA, then AA, and finally AA, right? So these are the three way outs. Now imagine how can we distribute them, right? Is there a way out or an easy way out? Let's write three ice creams here. So, or rather two ice creams here, right? AA. Now if we introduce a blind, right? Let me introduce a blind by a hash symbol, sorry, a backslash symbol. So I can introduce a blind here, right? Which means Sun 1 does not get anything and Sun 2 gets all the things. Then there can be a blind which is like this, which means each of them get 1, and finally there is a blind which is like this, which means Sun 1 gets both the things and Sun 2 gets nothing, right? So there are three ways of placing this blind, right? Or how do we do that? Let's make it a bit complicated. So if you have three things, A, and you have to divide it amongst two people, or among three people rather, right? So which means you would require how many blinds? You would require 2 blinds, right? So you can place first blind here, which means Sun 1 gets nothing, and second blind here, right? Which means Sun 2 gets 1 and Sun 3 gets 2. Or you can do is you can place both blinds here. So this is the first son's share, this is second son's share, and this is third son's share, which means third son get all the 3. So what are we essentially doing, right? if there are r people and there are n identical objects, right? So let's say a a a these are identical, so let me not make it capital. So a. So these are n identical objects, they can be ice creams or whatever, and we have to divide them in r amongst r people. So how many blinds do we need? We would need r minus 1 blinds, right? So let's put blinds by x. So let's say we have to distribute this amongst 4 people. How many products do we have? 1 2 3 4 5 6 7 8 9 10, right? So if we have to distribute 10 products amongst 5 people, we would need 4 blinds, right? 10 identical products. Please keep in mind that we are talking about identical products. So what is this? This is nothing but arranging these 14 objects, right, which can be done in 14 factorial, out of which 4 are of one kind and 10 are of another kind, right? So our answer would be 14 factorial divided by 4 factorial divided into 10 factorial. So this is the number of ways of distributing 10 identical objects amongst 5 people, right? Can we write it as 14C5, 14C4 rather? Yes, this is nothing but 14C4, right? Or this can be written as n plus r minus 1 C r minus 1, right? So this is the formula of distributing n identical objects amongst r people, right? You can either remember this, or if you understand the logic, it would be always better to remember the logic, right? So if there are 10 identical objects, we have to divide them amongst 4. How many blinds do we need? We need 4 blinds, right? So total number of objects would become 10 plus 4 14, and this divided by 4 identical blinds are there and 10 objects are of similar kind. So 14 divided by 4 factorial into 10 factorial, right? So this would be the answer if we are trying to distribute this in a way such that the possibility is there that few of them gets nothing, right? There is no condition, so there would be cases that few of them gets nothing. Now the next question says 3 ice creams are there, you have to distribute them such that in 2 suns, such that each of them gets at least 1, right? So since they are identical, what you can do is you can either give 1 ice cream to 2 suns, the remaining 1 is left, right, which can go in 2 ways. It can go to either sun 1 or sun 2, right? So this is one way out. The other way out is, let's make a table first. So it's S1 and S2, right? So it could be A or AA and A. So there are only 2 way outs, right? So what I was suggesting is you first give 1 to both of them, 1 to this, 1 to this. The remaining left is just 1, right? So it can go to either S1 or S2, right? So there are 2 number of ways. Or if we use our method of blind, right? Let's use the method of blind to understand this, and let's increase the number as well. So let's say there are 5 things. So A, and A, and we have to distribute them in three people. Now our blinds cannot come here and here, right? And our blinds cannot be like this as well, right? This means 1 is given to S1, 0 to S2 and 4 to S3, right? So our blinds can come in simple way. So if these are 5, our blinds can come in either here, either here, either here, either here, and only one blind at each of these positions, which means out of 4 positions we have to choose 2 blinds, right? 2 positions we have to place 2 blinds, which can be done in how many ways? It can be done in 4C 2 ways. So it would be 4C 2, right, which is equal to 4 into 3 by 2, 6 ways, right? The previous question says there are 3 objects divided among to be divided amongst 2 people, which means 3 objects A, and A, and 2 people mean 1 blind, so our blind can come either here, which means S1 gets 1, S2 gets 2, or our blind comes here, which means these 2 are with S1, this one is with S2, right? Which means 2 out of these 2 we are selecting 1, so 2C1, which is 2. So if you just look, what formula do we get? We get it as n minus 1 C r minus 1, right? So n minus 1 C r minus 1 is the formula when each of them gets at least 1, right? Or we can say when zero solution is not possible, right? So the answer would be n minus 1 C r minus 1. Mind you, the things should be identical in this case also, otherwise this formula would not work. I hope that you understand the logic behind this formula as well. So the next few questions are the same, right? First question says, in how many ways can you distribute 100 chocolates, 100 same chocolates amongst 10 students, right? So there are 100 similar objects. You have to place 9 blinds, right? No condition is given. So you can make 109 objects such that 100 are of one type and 9 are of another type, and get an answer as 109 factorial divided by 100 factorial into 9 factorial, right? So this is the answer for this question. In how many ways can the same question such that each of them gets at least 1, right? So we have 100 objects, which means 99 spaces in between, so it has to be 99C9, right? Out of those 99 spaces in between, we have to choose 9 so that it is divided amongst 10 students. Right? Next question is also very common, which says find the positive integer solution of a plus b plus c plus d plus e is equal to 20. So this is nothing but distributing 20 objects, right? So let's mark the objects with X. So there are 20 objects amongst 5 students such that each of them get at least 1, right? So we have to place 4 blinds in between the 19 spaces, right? So how can we do it? We can do it as 19C4, right? So this would be the answer. The next question says non-negative integer, which means 0 is allowed, which means we have to do arrangement of 20 plus 4, 24 objects such that, so 24 objects which can be done as in 24 factorial ways such that 4 are of one type and 20 are of another type, right? So this is done in 24 factorial divided by 4 factorial into 20 factorial, right? So this is how we do the distribution questions. I hope that you understood both the formulas as well as the logic behind the formulas, and if you are clear about the logic, you can solve any of the questions, right? So for example, let's take a question which is quite different from what we are doing till now. right? How many terms are there in a plus b plus c plus d raised to power 20, right? So if you have to find the number of terms in this, one method is there is formula, the another method is we can use the distributions, right? So any term is something like a raised to power a, b raised to power b, c raised to power c, and d raised to power d, right? Any term in the expansion of the series is something like this, where a, b, c, d can take values from 0 to 20, and the a, b, c, d's, these upper a, b, c, d's are, or let me use the capital letters for them, right? A raised to power a, b raised to power b, c raised to power c, and d raised to power d. So these capital A, B, C, D's can take values from 0 to 20, right? Such that a plus b plus c plus d is equal to 20 as well, right? In each term there could be a, b, c, d such that a plus b plus c plus d is 20, which means it's similar to finding non-negative solutions for a plus b plus c plus d. And how many non-negative solutions are there? It would be, so we have 20 to be divided amongst 4 people, so it would be 23, right? Or it would be not 23, so we have 3 blinds, right? So 23 factorial divided by 3 factorial into 20 factorial. So these many terms would be there in this expansion, right? So this is all about logic and counting, right? If you understand the logic, you would be able to count the terms as well, or you would be able to answer the questions which you have not solved previously, right? So the most important thing is to understand the logic behind the formulas, right? I hope that you are clear about how the formulas are made. So this is all for our session on permutation and combinations. I think the level of difficulty would not be greater than what we have done, right? There would not be any questions from topics like de-arrangements and all that stuff, so do not clutter your mind by reading all that stuff. If you can do these concepts very diligently, I hope that you would be able to solve more than 90% of the questions from permutations and combination chapter, right? So this is all about permutations and combination. I hope that you enjoyed the session, and I wish you all the best for your preparations. Thanks for watching this video.